Control strategies of plug-in hybrid electric vehicles. The plug-in hybrid electric vehicle operation modes can be either manually or it can be automatically mode based on the feedback signals of the various vehicle systems. The various signals would be the battery SOC, battery state of charge, power road load signal, expected trip length, and various other factors. In terms of control strategies, there are two methods typically applied for the plug-in hybrid electric vehicles. The first control strategy is AER focused, that is the all electric range control. The second is blended control strategy, where it can be the combined one. The all electric range focused control strategy for plug-in hybrid electric vehicle. This AER mode of control takes the advantage of electric power and runs the vehicle in all electric range mode, that is on the battery powered mode, before the battery SOC drops below a certain level, that is a threshold level. After that, the engine starts and the system operates in the charge sustaining mode, that is the CS mode. The all electric range mode based control strategy is to prioritize the fuel reduction and emissions reduction in short range trips by running exclusively on the battery power. So the emission reduction and fuel efficiency is focused. It is more suitable for city driving and short range suburban driving, where daily round trip distance is within the electric range and a lesser distance. Since all the power in all electric range mode comes from the battery, that is the electrical systems, batteries with large energy capacity and electrical machines and power electronics with high power density are required to satisfy the drive performance requirement. So ratings of these components will be sufficiently large in AR mode. Another is the blended control strategy. The blended control strategy utilizes both the engine and the electric machines to power the vehicle as compared to the earlier AR mode, where in the earlier mode, the focus was to use the electrical energy only, but here both the engine and electric machines are operated. On the basis of the expected travel distance, the blended control strategy picked the most appropriate fuel efficiency combination, fuel or electricity combination, that is the IC engine or the electric motor combination, so that the battery SOC decreases smoothly in a linear trend and there should not be drastic depletion of the state of charge of the battery. So the support of the IC engine is also taken. The blended strategy, the vehicle operates under CD mode with the engine running in its high efficiency region all the time till the battery SOC drops below certain preset level. After that, the vehicle operates in charge sustaining mode. The blended control strategy prioritizes the range extension. It achieves an extended range in the charge depleting mode by using either the engine dominant strategy or the electric dominant strategy. So the blended control strategy will make the use of both the available options, that is IC engine or electric motor. In short, The optimum control strategy should rely on the trip distance that one PHEV is going to travel. If the trip distance is within the battery all electric range, then air focused control strategy should be applied to achieve the maximum fuel displacement. Secondly, if the trip distance is greater than the electric, that is all electric range, the blended control strategy is preferred with the engine running in its high efficiency region throughout the trip so that optimum fuel efficiency can be obtained. Electric machine operates frequently in the low speed regions under the local driving scenario, while it operates more frequently in the high speed regions on the highway. So electric machine should be operated at low speed regions. Electric machine operates frequently in the negative torque region under local driving so as to retrieve more regenerative braking energy. So regeneration is one of the features that can be achieved in the control strategy. For both local and highway driving, engine is largely controlled to be operated at high efficiency level so that it can achieve the better efficiency. Different control strategies will result in different operation points for both the engine and the electric machine, and they can affect the fuel consumption as well as the emissions of the vehicle. So control strategy should try to increase the range, efficiency, and lesser emissions. Plug-in hybrid related technologies and challenges. Here we'll discuss the PHEV related technologies and challenges. The PHEV employ large set of electrical power systems with electricity serving as the primary power source and electric machines as the primary propulsion drives. Engine and fuel tanks are written on board, so they are available. So both options are available. But they are downsized. So engine is downsized to smaller scales and only they assist the motors and batteries with additional power and additional drive range. So the main function of the engine is to support the electric mode. All the changes bring the higher standards for the electric power system, including battery, electric motors and generators, power electronics, and their related controls. Massive component changes also require different platforms or even the reconstruction of the mechanical drivetrain. In addition, PHEVs change the way of refueling the vehicles, which enables drivers to charge the vehicle at home from grids instead of looking for public gas stations or refueling stations. However, this also brings a concerns in regarding to the grid's capability as well as the installation of power charging outlets and public charging processes. So the challenges are relating to the providing the charging infrastructure. Considering the above facts, there are four main areas of challenges if we consider the plug-in hybrid electric vehicle challenges. The first is plug-in hybrid electric vehicle batteries and related challenges. Second is plug-in hybrid electric vehicle cost and related challenges. Third is plug-in electric vehicle charging and challenge. And fourth one is plug-in hybrid electric vehicle and the grid-related challenges. Here we'll discuss these PHEV related challenges one by one. The first is plug-in hybrid electric vehicle batteries. If we consider the batteries, we can see the important points are there should be high performance battery. Batteries with large energy capacities are also highly desired in plug-in hybrid electric vehicle because the battery size and the battery Rating is the important thing when we consider the plug-in hybrid electric vehicle because they have to store large energy, large capacity of the battery, and they should provide the required energy. Battery energy capacity directly determines the extent of which all electric driving range will be determined, in which the degree of the displacement of fossil fuel and emissions reductions are also considered. If the battery size is large, it can provide the larger driving range and corresponding there will be reduction into the emissions and also lesser use of the fossil fuels. From the consumer's point of view, more energy that the battery carries on board, the range anxiety will be lesser and the owners will be confident about the range if the battery size is larger and sufficient battery size. The large battery energy capacity also provides sufficient energy for accessories of the vehicle such as air conditioning, then lighting, other radios while they are on the AR mode. The another concern is the battery power density, and that is also area of challenge in PHEV. Battery power density defines the maximum power that the battery can supply to the vehicle in terms of certain weight or volume. We are considering the battery power per unit weight or per unit volume. It largely contributes to the acceleration time that the vehicle needs from the speed 0 to the demanded driving speed with the engine turn off. Power density is responsible for the acceleration of the vehicle from 0 to the required speed. The power density determines the maximum torque of the vehicle, that is the output from the electric power system when sudden acceleration is required. So power density should be sufficient to get the maximum torque in a required time. Both large energy density and high power density are demanded in plug-in hybrid electric vehicles to achieve the desired high standard plug-in hybrid electric vehicle performance and the operating functions. These high requirements, that is the power density and energy density, increases the battery cost and thus the overall plug-in hybrid electric vehicle manufacturing costs are increased. Thus, the challenge is how to reduce battery cost while improving performance is the great challenge in the battery technology, and that has to be addressed. The increased battery requirement also leads to the increase of battery size, battery weight, and which reduces the vehicle dynamic performance as well as the fuel economy. So it is important to achieve a low size battery, a smaller volume battery, but at the same time there should be large energy density and high power density. High power density is often achieved in advanced battery technologies by using thinner electrodes and is typically realized by implementing thicker electrodes. That is, high energy densities realized by implementing thicker electrodes, and high power density is realized by using thinner electrodes. The development of high performance batteries still is a challenge of improving the power density and energy density, and that is the area of challenge. The next is discharge cycles of the batteries. Batteries in plug-in hybrid electric vehicles have to go through repeated charging and discharging, and these are the deep charge and discharge cycles, as well as a number of shallow charge discharge cycles in both charge depleting mode and charge sustaining mode for power assistance and regenerative braking. This brings high standards and great challenges in the battery technology development so as to meet the typical 8 years to 80,000 miles automotive battery warranty standards. So discharge cycle has to be a larger one and improved one. The next challenge related to the batteries is the safety and reliability of the batteries. High voltage and high current components should be carefully packed and isolated from the chassis and accessory systems. The coolants are needed and should be regularly maintained to keep the working batteries in safe operating temperature so that there should not be any heating problems, explosion of the batteries, or any hazard related to the battery because of the temperature. The hazard protection method should be also taken into account while designing and manufacturing the batteries into the processes. Batteries applied to the vehicle are not only required to safe for drivers and passengers during the driving process, but they should not also cause any hazard situation in the maintenance and repair of the vehicles. Thus, it is necessary to keep all high voltage components labeled, fused, and well insulated to reduce the risk during the maintenance. Appropriate safety gear such as safety glass, insulating boots, and insulating gloves are required dealing with the batteries. The risk surrounding batteries during accidents or collisions should be reduced to minimum level when plug-in hybrid electric vehicle configurations are designed. Also, trainings of emergency responses should be provided regarding the high voltage battery and the electric system. The codes and standards established to address the technical issues related to the plug-in hybrid vehicles are also required. For example, in US, the list of SAE and NFPA codes and standards are applied to regulate PHEV vehicle safety, emergency response, and infrastructure safety. The next challenge is the PHEV cost, plug-in hybrid vehicle cost. The large demands for battery energy capacity and power density require a remarkable quantity of batteries, which account for substantial part of the cost increment. The large torque and speed requirements of the electric motor and generator also add considerable manufacturing cost due to high powered electric machines and power electronics in the vehicle. The PHEV reconstruction, large battery pack installation, integrated transmission powertrain, added electric motor generators, and the control power electronics all require 3 days of the vehicle chassis to accommodate these added components and their corresponding weights. Next is the safety components are required to add onboard vehicles to prevent the hazardous situations regarding the electric power system. High voltage shutdown mechanism is required to prevent battery fire during the vehicle crash and in the event of airbag deployment. Maintenance of the electric power system may add potential cost. So all these points increases the cost of the vehicle. So in short, torque and speed requirement, the electric motor cost, the plug-in hybrid electric vehicle component cost, the safety concerns and related cost, the high voltage shutdown mechanism, and related cost and maintenance cost. So all these costs add to the overall and total cost of the PHEV. Diagnose and repair also become more difficult due to the more complicated powertrain integrated by the mechanical power path and the electric power path. As the both sources are acting, the control is there. So this also incur a larger cost. Another major component of the cost is battery replacement cost within the vehicle's driving life, also bring a substantial maintenance for the owners. Next is the reliability of the added electric system in PHEV is critically desired to bring down the overall cost of the PHEV. So reliability has to be also maintained. The third one is the charging of PHEVs. Plug-in XCT charging includes charging strategies, charging types, and corresponding charging infrastructure. The first is the charging strategies. The charging strategies greatly influence battery SOC and all electric trip range based on the fixed battery and energy capacity. The first scenario in the charging is the driver charges the PHEV whenever the car is parked. That maximizes the all electric driving range and achieves the fossil fuel displacement or reduction, lesser use of the fossil fuels. It can be applied on daily driving where the recharging access can be found at workplaces, parking lots, grocery stores, and so on. The second scenario of charging is recharge the PHEV once, charge the PHEV once every night. When the vehicle is typically parked at home and the price of the electricity is relatively low, so charging at low rates or when it is a off-peak period. This enables drivers to recharge their vehicle in the garages or somewhere near their home while they stay at home or sleep. The third scenario of this is charging is recharge the vehicle during the lowest utility load demands. It helps to balance the grid utility loads and achieve the maximum savings of PHEV owners because the rates are lower. This requires control and communication between the vehicle and the grids, and the battery may end up without being fully charged. As the setting may be there based on the price or when there is a lower demand, then the control system may switch off the charging of the battery if the prices goes up. So this has to be considered while putting the third scenario. The fourth commonly used scenario is recharge the plug-in hybrid electric vehicle at any time and at any day. This charging method is also called unconstrained charging. The conventional way that people fuel up their petroleum-powered cars, and it offers the largest freedom to the drivers in terms of recharging schedule. It greatly requires a quick charging speed so that PHEV drivers would not feel uncomfortable waiting at the charging stations for a relatively long time. The charging levels of different charging scenarios can be the following one. The first level is the home charging level. The PHEVs are generally charged by the home power outlet, such as garages. The second level charging, it supplies higher charging voltages and currents so that the charging time will be reduced. It's typically used by implementing high power charging equipments that boost the voltage and current output. The third level, this is the highest charging level, which carries hundreds of volts, that is a kilovolts, and hundreds of ampere, that is a kiloamperes. That is a high level. It significantly reduces the charging time because of the larger ratings of the voltage and high current levels. So charging time is reduced to the level that is competitive with the conventional petroleum refueling or refueling the diesel and petrol. The third charging level is typically applied in public charging stations where fast recharging is mandated and safety is prioritized. The next is now the plug-in hybrid electric vehicle and grid challenges or related grid challenges. Grid capacity is the potential issue with the increasing use of electricity displacing conventional fossil fuels. Plug-in hybrid electric vehicles will bring in a large amount of utility load increase since electricity serve as the primary energy carrier to meet the driver's daily trip demands. So plug-in hybrid electric vehicle will require large amount of charging and it will be one of the large amount of load on the system. The grid should be able to tolerate the maximum utility loads when the worst scenario happens. That is, when all plug-in hybrid electric vehicles and even electric vehicles are plugged into the grid at the same time. So the grid has to sustain or tolerate this plug-in hybrid electric vehicle charging load. Second, in the increase of overnight utility loads caused by plug-in hybrid electric vehicle, night recharging may result in the change of the control strategies to manage the balance. So grid balance has to be maintained properly when the charging is done by the PHEVs. Real loads hit a valley or down at night when most people are asleep and household utilities are turned off. With the increase in PHEVs, more electricity will be consumed during the night hours because the vehicle owner will prefer to charge the vehicle at night hours because of the low rates. Control strategies to balance utility loads will need to adjust accordingly. So this increased load at night or off-peak hour need to be balanced appropriately. The grid may also implement V2G, that is vehicle to grid technology, to take advantage of the plug-in features so that the battery power of PHEV can be turned back to the grid. Thus, in V2G mode, the battery can supply to the grid when the load demand of the grid is more or it is at the peak when the vehicle is parked. This can also, the vehicle will work as a source to the grid. The vehicle to grid technology helps to balance the grid loads and reduce the utility expense for PHEV owners. Obviously, they are getting the benefit by supplying energy to the grid from their vehicle battery or plug-in hybrid electric vehicle battery. Besides, the vehicle batteries can also be used as a backup power storage to send power to the homes in case of the utility is temporarily out of service. So it can be a backup for their houses. The vehicle to grid communication requires new grid technologies such as implementation of smart meters, new power distribution, and control strategies. So these are the major challenges. Thus, in this point, we have discussed about the various challenges related to the PHEV. That is the PHEV challenges related to the batteries, related to the cost, related to the charging, and related to the grid when they are connected to the grid to charge and also to discharge into the grid.